In a prior video, we had discussed the concept of bond polarity, meaning that covalent bonds could be either nonpolar or polar depending on the difference in the electronegativity of the two elements that make up that covalent bond. Now, the bond polarity is actually important because it eventually would lead to determining whether the molecule itself is polar or nonpolar. And why is that important? If you have molecules that are polar and nonpolar, they will not mix. Here's an example. Water is a polar molecule and oil is a nonpolar molecule. Oil and water don't mix. So going back to this concept of molecular polarity, what we just discussed about mixing is very relevant because if we have a polar molecule, then it will mix with another polar molecule. Whereas if we have a nonpolar molecule, then it will mix with another nonpolar molecule. Whereas a polar and nonpolar molecule will not mix, which is like oil and water. So what we want to do here is to use our Lewis structure and our VSEPR information to help us determine whether a molecule is polar or not. And there is actually a way to do this mathematically, but in this class we're just going to use relatively simple set of rules to help us determine whether our molecule is going to be polar or nonpolar. So first you look at the bonds. If the bonds are all nonpolar, then we would assume that the molecule is nonpolar. And again, the way you figure that out is by looking at the electronegativity difference of the two elements. Now, if the bonds are polar, then we have to look, are the terminal atoms identical or not in this case? If the terminal atoms are identical and if there are no lone pairs, then the molecule is nonpolar. However, if the terminal atoms are identical but there are lone pairs, then the molecule is polar. Lastly, if the bonds are polar and the terminal atoms are different from each other, then we have a polar molecule. I want to work through a few examples of assigning molecular polarity to different types of species using the rules we discussed in the note. The molecules and ions I want to use as an example is listed here. And let's start with POCl3. The first thing you have to do is draw your Lewis structures. Let's go with assigning the number of valence electron. Phosphorus has 5, oxygen is 6, chlorine is 7, and there's 3 of them. So that ends up being 32 electrons. And again, just a reminder, group number for each of the element equal the number of valence electrons. The next step is to start with our skeletal structure, and phosphorus being the least electronegative atom would be the central atom, and the other atoms are just going to be around the phosphorus atom. It doesn't really matter where you put the chlorine versus the oxygen. So starting with this, we already used up 8 of the electrons, so we're going to subtract 8 from our total electrons, so we have 24 electrons left. And like usual, we would assign all the terminal atoms to be octet and see what happens after that. That means 6 for each terminal atom, and 6 times 4, because there's 4 terminal atoms, is 24, and so we end up using all of it. Now once we have that, here's where we're going to go to the polarity steps that I was discussing earlier. So the first thing is we need to determine what kind of bonds we have in the molecule itself. You have 2 types of bond. You have a bond that's formed by P and Cl, and then you have a bond that's between P and O. So there are different types of bonds. Now the question is, are these bonds polar or nonpolar? So in order to be able to determine that, you're going to have to look at your electronegativity values. Here I have my electronegativity table, and what I need to take a look at is what is the difference in electronegativity between P and O. That's one of my bonds. So P is 2.1, O is 3.5, so the difference of the two is 1.4, and that tells us that that's a polar bond. If you go to P and Cl, Cl is 3, P is 2.1, and if you subtract those two, you're going to get 0.9, and that's also polar. All the 4 bonds we have here are polar bonds. Going back now to our polarity determination, if you look at step B, it says if the bonds are polar, are the terminal atoms identical or not? In this case, they're not, because 3 of the terminal atoms are chlorine and 1 is oxygen. So then we look at C, it says bonds are polar and terminal atoms are not identical. The molecule is polar. So we would assign this to be a polar species. Let's now go to the second example, SO3 2-. Start with valence, 6 for sulfur, 6 for each oxygen, and there's 3. And then it's an ion, and it has a 2 negative charge, so plus 2 more. That gives us 26 electrons. Sulfur is our central atom, 3 oxygens. That uses up 6 electrons, so 20 electrons left. Assigning the terminal atoms to be octet requires 6 electrons each oxygen atom. And 6 times 3 is going to be 18, so 2 left. That 2 can be placed on the sulfur to make the sulfur octet, so we use up all the electrons we have. This is an ion, so don't forget that you need to put a bracket and a 2- on the outside. Now, we go back to our polarity determination steps. First thing is, what kind of bonds do we have? Well, all the bonds are the SO bond. So what we need to think about is what kind of bonds is an SO bond. We will look at the electronegativity difference between S and O. O is 3.5, S it's 2.5, so the difference is 1.0. That's a polar bond. So we're back to the polarity rules. There's 2 situations when bonds are polar. You could either have terminal atoms that are identical or not. In this case, all the terminal atoms are identical. They're all oxygen. We do have a lone pair on the sulfur. So it says here, if there are lone pairs, then the molecule is going to be polar. So this one is also polar. So take a look at SCl2. The valence electron is 6 for sulfur, 7 for each chlorine, and there's 2 of them. That ends up giving us 20 electrons. Sulfur is the central atom, resulting in that skeletal structure, minus 4 electrons, leaving us with 16. And putting 6 on each chlorine to make octet uses 12 electrons, so 4 left. That 4 has to go to the central atom to make it octet as well. So we use up all our electrons. Going back here to our polarity rules, first we look at the type of bond we have between S and Cl. S is 2.5, Cl is 3.0. So the difference is 0.5. 0.5 is also still a polar bond. So we have 2 polar bonds in there. Now going back to our polarity determination rules, we see that we have a polar bond and then we have identical terminal atoms. So in this case, we have lone pairs, so then this molecule is also going to be polar. We're going to continue with 2 different species. One is CH4 and the other one is CO32-. We're going to start with CH4. Valence electron is 4 for carbon, 1 for each hydrogen, then there's 4 of them, so that ends up being 8 electrons that we have to assign. Carbon is our central atom. Remember, hydrogen has to be the terminal atom, and there's 4 hydrogens, so we're going to put it this way. You've used up all the electrons that you have, which is 8 electrons, so you're left with nothing. And that means that that should be complete. Now, one thing that's important to check at this point is to make sure that everybody satisfies the octet rule. And the carbon obviously does. Hydrogen, remember that to satisfy the octet rule, it needs to match the configuration of the noble gas that's closest to it, which is helium. So it has 2 electrons. So at this point, hydrogen is also complete. So the next thing is to determine what kind of bonds we have. And if we look at the 2 atoms that we have, carbon has an electronegativity of 2.5 and hydrogen has an electronegativity of 2.1. So 2.5 minus 2.1 gives us 0.4. And if you remember, our electronegativity rule tells us that if the difference is up to 0.4, then that is going to be a nonpolar or pure covalent bond. All 4 bonds here are nonpolar bonds. And we see that if all the bonds are nonpolar, then the molecule automatically is also nonpolar. So we would assign this molecule to be nonpolar. Let's take a look at another example. CO32-. This is an ion. Start with valence as usual. Carbon is 4, 6 for each oxygen, and there's 3 of them. And don't forget this is a 2- ion. That means you need to add 2 more electrons. And that would give us 24 electrons. Carbon is our central atom, and we have 6 electrons, which leaves us 18 electrons to put in the rest of the structure. Making the terminal atoms octet requires us to add 6 electrons each oxygen, and 6 times 3 is 18 electrons. So at that point, we're done. Now, when you look at the structure right now, we can see that the structure is not octet for all the atoms. Specifically, the carbon atom in the middle is still not octet. It only has 6 electrons. So I'm going to need to do a double or triple bond. We can move a pair of electrons from any of the oxygens. So I'm going to take the one on the left and make that a double bond. And right now, all the atoms would be octet. Since this is an ion, I'm going to complete my structure by putting a bracket around it and putting a 2- on the outside of the bracket. And remember that this counts as one effective pair. So we have 3 bonds, and all the 3 bonds are CO bonds. If we look at the electronegativity table, we see that C is a 2.5 electronegativity, and oxygen is a 3.5 electronegativity. So the difference between C and O is 1.0, which means it's a polar bond. So we have 3 polar bonds. All our terminal atoms are oxygen, so they are all identical. And then the next question is, do we have lone pairs or not in the central atom? In the structure of carbonate that we drew, there are no lone pairs. If there are no lone pairs, then the molecule is nonpolar. I want to point out that it doesn't matter whether you draw that double bond on the left side as I did, or you move one of the other pairs of oxygen to make the double bond. So for example, it's completely possible to draw carbonate this way, and there's nothing wrong with that. You still have octet for everybody, and the structure is still correct. When you go through that entire molecular polarity exercise that we just did, you're going to find exactly the same answer, which is that this is still going to be nonpolar. So it's not going to change your answer whether you draw the double bond on the left, as I did, on the right, or as you can tell, you can also draw it in the bottom, right here.